In this quick video, I want to talk about some important pKa's. And so pKa's are, and where we can get these values, so pKa tables and I suppose pKa values in general. And so what I want to start about is these are very useful for predicting acid base reactions, and in particular we focus there on the equilibria or the equilibrium constant. But without getting too deep, what I want to do is just mention a few useful pKa's to sort of have in your back pocket. If this were a course with like quizzes and exams, I would say let's have a quiz or exam where we just see how many of these we can, how many of these important ones we can memorize. And so acetic acid is a nice baseline pKa with a value equal to 4.7. We had talked about this one in organic too, but in the context of a lot of other pKa's. So I think it's helpful to kind of see it. Pyridine is a useful base, so that's benzene with a nitrogen in it. So pyridine is a useful base, but the issue is that it it doesn't itself have a pKa. What we have to consider is the protonated version or the ammonium salt. So this is the this has a pKa equal to 5, and knowing this pKa helps to see why the base pyridine is a good base. Particularly in reactions with carboxylic acids. So if you introduce some electron withdrawing groups on a carboxylic acid, further reducing its pKa, sometimes down in the neighborhood of 1, pyridine is sufficiently basic enough to deprotonate it, because the protonated form, the ammonium that I have drawn here with the nitrogen with a positive charge, is a pKa of 5. So the fact that it has a higher pKa than the carboxylic acid means that it will react with and deprotonate that carboxylic acid with a fairly favorable equilibrium constant. Okay? Let's actually draw out some reactions for this. So if we have this as our acid and its pKa is equal to 4.7, and we put it in the presence of the pyridine base, we let those two react with each other. We could say that because the protonated pyridine, the conjugate acid of pyridine itself, has a higher pKa, the equilibrium shifts, and this is favored, probably not favored to that extent, but if we reduce that pKa of the starting carboxylic acid even further, we would favor this even more strongly to the right. So we can get an idea of what the equilibrium constant will be by comparing pKa's. Now it's pretty useful for acid-base reactions, because the transfer of a proton in an acid-base reaction is generally very fast. You don't have to worry about kinetic effects as much or as often. But if we compared a different acid source, like cyclopentadiene anion, which last time we said had a pKa equal to 15. Now, if we let that react with pyridine, we would see virtually no reaction in the forward direction, because the pyridine conjugate acid has a much lower pKa. So the equilibrium generally tend toward the acid, the conjugate acid with the larger pKa. So this one is favored to the left. So understanding these pKa's is really helpful for predicting equilibria. Like for example, you still wouldn't use triethylamine. So would another common base that we used in carboxylic acid chemistry was triethylamine, often abbreviated as TEA. So would this one work? Well, let's take a look. So here's triethylamine. Now we can't get a pKa reading from this. Just like pyridine, what we want to do is look at the conjugate acid and see how its pKa, or see where its pKa is at. So the conjugate acid of triethylamine looks like this, and its pKa is equal to 10. So for many carboxylic acids that might be a little, have too high of a pKa because they have some electron donating groups present, triethylamine might be much better than pyridine because its corresponding ammonium salt has a pKa that's much higher, driving that equilibrium further towards the deprotonation reaction. However, it's not strong enough for and who's not strong enough? The conjugate base for deprotonating cyclopentadiene, which has a pKa of, in its anionic state, is equal to 15, as I mentioned earlier. Okay, so just getting a reading of pKa's, we can already understand a lot about important reactions, in particular where equilibria will lie. And that's really crucial for understanding some basics of some basic aspects of some of these more complicated reactions. So where are some other important pKa's? Well, I might consider a malonate, which is a dicarboxylic acid ester. That's an interesting one. It has 2 carbonyls, and its pKa is equal to 14. And then the other one I want us to pay attention to is water. Water has a pKa of equal to 15.7, and ethanol has a pKa equal to 16. Okay, some of you might be thinking, doesn't water have a pKa of 14? Well, we can talk about that, but let's stick with 15.7. Now, let's think about where we get these values. So I'm just springing these values on you. I think it's important to recognize that triethylamine is a pKa in the ballpark of 10 when it's protonated, pyridine 5, carboxylic acids 5 and lower, water's 15.7, alcohols increase that a little bit up to 16 in the case of ethanol. Those are some really nice pKa's to hold on to, particularly like ethanol, for example, or just an alcohol being about 15 to 16, depending on the substituents that are present. But what if I want a specific pKa value for something more complicated? So I've got my internet browser open behind us. So there are several resources. You could search the Bordwell pKa table. This has got many different groups. You can see some of these things that we had mentioned before. Let's first of all get this. So this is the equilibrium pKa with H2O as a solvent. So these things demonstrate a lot of solvent effects, but here's the pyridine that's been protonated at 5.2. So I think I said 5. So maybe a subtle difference, but you can get an idea. Now let's see if we can find the protonated triethylamine. So this is diphenylamine. Here's imidazole. Here's ethylamine, diethylamine, and triethylamine. So triethylamine, it has at 11. So maybe I had a DMSO value. Huh. Wonder where I got that number. So the other one is the Evans pKa table. And these are just easy Google searches to find. So the Evans pKa table is kind of a nicer PDF, but it doesn't have as many values. Let's see if we can find. So we have H2O, water is 15.7 or 32, and the other common solvent to measure these things, which is DMSO. And then, let's see, protonated nitrogen. So here's triethylamine with the proton, 10.75. And my value was, just looking through my notes. Oh, I said 10. Okay, so maybe I should change that to 11. Small difference, but you know, those pKa effects can be quite substantial, but just having a ballpark idea is important. Let's look for some other ones. So We have carboxylic acid 4.76 for acetic acid, but then the substituents kind of set the deal, so you can see these things really drop if you introduce electron withdrawing groups. Let's try to find alcohols in the Bordwell pKa table. So we have these convenient sort of just listings of all of the things. So here's cyclopentadiene is in the hydrocarbons. Here's cyclopentadiene, so they have 18. So maybe these things are going to, and I said 15, maybe these things are going to change a little bit. I wonder if I'm questioning where I got some of my values. That's why it's almost doubly important that I introduce this list for you, so you don't have to take my words at face value. Okay. Oh yeah. So in the Evans pKa table, they say 15. Let's see, alcohols. So this is in, these are in DMSO. pKa values in DMSO by functional group. Huh. Well, it's helpful to have multiple solvents, I guess, but I wonder where the alcohol is in, in pKa values in water. Oh, maybe it's just limited to these. All right. So there's, that's a protonated methanol. Okay, well, I don't want to waste any more of our time discovering all of this stuff that I should have been more familiar with. I'm more of an Evans person myself. I like that pKa table a little bit, just it's a little bit more digestible, and usually you aren't working with a molecule that has a known pKa, so just getting a ballpark idea quickly on the Evans table can be helpful, but definitely the Bordwell is more comprehensive and probably more updated with references. So anyway, we'll end the lecture there. So this was a sort of a warm up into pKa's for the purposes of this class, as opposed to, the purposes for more rigorous courses in acid-base equilibria like quant and that sort of thing.